Today, we're going to be talking about service architectures for mere mortals. Now, I say mere mortals and not something like service architectures for dummies because nobody here, either in this room or watching the video later, is a dummy for not knowing this. This stuff is very complex. We're all trying to get through, we're all trying to do a very complicated job where the answer to every question is, it depends. And so we're going to, so it's okay not to know a lot of these things. So we just recognize that we are all mere mortals in here. So some of the things we're gonna go over today are what service-oriented architecture is. We're gonna compare that with our traditional Rails monolithic app. We're going to look at some communications patterns between these decentralized systems, decentralized services, and some of the trade-offs of going from choosing one pattern over the other. So to start off with, what is service-oriented architecture? The problem is, there is no single definition. So I say that's a problem, but it's actually, there are good and bad things to it. Let's start off with some of the downsides. One is that it's hard to Google. And it's not that you won't find any information about it. The problem is you're going to find way too much. You're going to find an overwhelming amount of information about service-oriented architecture, but a lot of it probably won't be something that's actionable to you as a Rails developer. And it's also hard to figure out what applies in your specific circumstances. Sometimes you'll get information that's too specific. Something is focused on a different ecosystem because service-oriented architecture is not it's not an overly common thing in a Rails ecosystem as it is in, say, a Java or a .NET ecosystem. And so you're probably going to find a lot of resources that are too focused on, I shouldn't say too focused. For the people that wrote them, they're not too focused for them, but they're too focused for somebody in the Rails ecosystem. And so when you find things that are too specific, you end up diving down a Wikipedia rabbit hole trying to map some of these concepts to something that we might find in a Ruby gem. Other times, you get stuff that's just too vague. It's too theoretical. It's so high level that there's nothing actionable in it, in these Google results. So, yeah, so a lot of times it's because they're trying to avoid the situation where they might end up being too specific. And then you get a lot of this, some of this other stuff about how if you're not doing services this way, then you're not actually doing services. There is an unfortunate amount of that out there in the service-oriented architecture Google results. The problem is that's unnecessary gatekeeping, and it falls squarely into the no true Scotsman fallacy, which is that if you aren't doing something a certain way, you're not actually doing it. Then it's not categorized as that thing. And so another downside is that there's no real convention around this. As Rails developers, we love our conventions. We like being able to install a gem, and we just get a lot of functionality out of the box. But there's no way to just say gem install SOA and you get a service-oriented architecture for free. So after I wrote that slide, turns out because I actually checked because I'm like, maybe somebody's done like a half-baked attempt at this. Sure enough, it was Justin Searles, and it's not even real. So so there again, so there is no real convention around this, but there are a lot of fun attempts at this, and there are attempts like conference talks like this one, and there have been a few at other Ruby-focused conferences about services, but nothing kind of like to get you going. There's a lot of stuff that's focused in different areas than maybe in your specific situation. But on the bright side, you're not locked into any specific into any specific implementation of a service-oriented architecture. And that's one of the really nice things about not having conventions, is that you have a lot of freedom. Anything that you end up incorporating into your system is not locking you into their implementation. So, but there are a lot of common patterns that you'll see in service-oriented architectures. The main one is that your Rails app that you're building is no longer the center of the universe. It's not the only important thing that you're working on. It's now just a single component of a larger distributed system. And it's, scratch that part. One pattern is that your services might serve up JSON or some other machine-readable format. And maybe the consumers of these services might be something that your end users are consuming from your API, and it might be something that your own services are consuming from other services inside your system. Sometimes they might serve HTML that's rendered from various parts of different services, and then all just kind of like bundled together to serve to your end user. Some of your services might run on Rails. Some of them might not be Rails. They might, for a much smaller microservice, you might be using something like Sinatra or Rhoda instead. And maybe they're not even Ruby at all. They might be when you're talking to a remote service, you don't have to use the same programming language for both sides of that conversation. You might use, for something that needs a lot more performance, you might use a programming language that has a typically more performant runtime, like Go or Elixir or Crystal. And maybe they don't even speak HTTP at all. They might talk over a different interface, and we'll talk a bit about that in a little bit. Some of your services could be stateless, which is just a fancy way of saying that they don't have a database. Usually when you're talking to a stateless service, you're actually telling it to perform an action. You're saying this, either I want you to do this, or this thing has happened and you should respond to it. On the flip side of that, if we're making a distinction about stateless, the opposite is going to be stateful. And so this is just saying that it is storing some sort of data somewhere. It might be storing it in a traditional SQL database. It might be storing it in some data on S3 or in Redis or some other sort of back-end store. But somehow it doesn't matter to you as a consumer of that service how they store it. You just need to know that you can fetch data from this particular service. If you're unsure, if you're building a service like this, and you're unsure what sort of database to use, the fact that I mentioned it doesn't have to be SQL database like Postgres. If you're unsure what to use, just use Postgres. Your ops people will thank you. And your services can call out to other services. You don't have to necessarily be the terminal point of that dependency chain. If somebody makes a request into your service and you don't have all the data inside of your own data store, maybe you can call out to some other services. This is actually a very common pattern. We'll talk about that in a little bit too. So that's a kind of high-level, very brief overview of what service-oriented architecture is. We're gonna go into a little bit more detail in the next section here, where we compare it and contrast it with a monolithic Rails architecture. So when we talk about monolithic architecture, so one of the things I wanted to do is I wanted to grab a definition from the dictionary, which is, as is tradition with dictionaries, the word is defined in terms of itself. So of relating to or resembling a monolith is the definition of monolithic. Thanks, Webster. But also notice that it says huge or massive. Those are two of the other adjectives that are associated with monolithic, which I thought was kind of funny, because monolithic Rails apps over time, especially over 5 to 10 years, will start to get really large and incorporate a lot of functionality. I also really like this definition. It's formed from a single crystal, like Ruby. But mainly, the definition is that you think of the application as one piece. There is only one thing that you're kind of developing, testing, and deploying as a single unit. But no matter what, a monolithic app, yeah, considers itself to be the most important thing in the universe. A lot of web monolithic apps are built with this idea encoded into itself, into its DNA. Whether that's explicit or implicit, whether it's intentional or unintentional, this is actually a really common pattern where if you decide to start separating things out later, this might get in your way. So while you're working on something like this, if you think that might be a possibility, that you might split things out into multiple services later, you might want to, as you work through your daily tasks, you might want to think about this, this particular part that I'm working on. Is this going to be something that would block us from separating this out? Another fun thing about monolithic apps is that they're not truly monolithic. And so let's go into what that looks like in this example. So let's say you have a user visiting your Rails app, right? User makes a request with the browser. Rails sends back a response. Seems pretty simple. However, we are overlooking quite a few things. There's a lot that happens in between. When that request comes in, we need to know what to send back in our HTTP response. So because our Rails app doesn't keep everything in memory or in its local file system, it has to reach out to something else. In that case, this is most likely our database. By convention, we're probably using some sort of SQL database on the back end. And then the database returns the query results to our Rails app, which then converts that tabular data that we get back from Postgres into something that our domain objects can handle inside of a Rails app, that we then package into HTML. So it probably seems pedantic to consider the database to be separate from the Rails app, because we normally think of, that's just part of the app, right? But bear with me for just a second. Your app might also send emails so that your users can receive things like receipts or notifications. But since we don't deal directly with SMTP, we're not actually processing that email ourselves. We're sending that off to a third-party email service. So we add a node for that in our graph here. And we don't want to send emails in the course of a web request because that takes too long. It adds too much latency to our response. So we actually want to kick that off to a background job. So we add a node for Sidekick in our graph. But our Rails server doesn't talk directly to our Sidekick graph, or to our Sidekick process. We're actually sending that into Redis, and Sidekick is reading from Redis. So we add a Redis to our graph. But we need to accept payments, so we add a payment processor. And any production system needs logging, error tracking, system metrics, and consumer-side analytics. And we may want to perform caching on certain resources to reduce latency under load or improve throughput. So we add a cache store to provide that for us. And we probably want to provide faceted and full text search, so we add a data store that provides that as well. And suddenly our monolithic, our single piece app now has 12 pieces. 8 of these can be considered fully fledged services. 2 of them we own, the Rails app and the Sidekick process. And the rest of them, all of the pink nodes on the graph, we integrate with over known channels, usually over HTTP. And the other 4 of them are their data stores that we use to generate our responses through our Rails app. And this is just the more common Rails app configuration. Nearly every Rails app I've ever worked with in production has this kind of structure. None of them are truly monolithic. And so really a monolithic architecture is more about centralization. The Rails app in this graph is really just the focal point for all of our stuff. Most of the data will end up passing through that Rails server at some point, whether it's coming through one of the data stores or we are passing it through to our email processor, things like that. Whereas service-oriented architectures are mostly decentralized. And I say mostly because there are a few particular components that nearly every service will need to talk to. In most Rails apps, we have a few of what are known as God objects, And usually these are things like your user model and whatever other model in your app that your business revolves around, such as products or orders for an e-commerce application. In a services approach, these God objects actually become their own full-on services, typically, that you end up needing to talk to. Every distributed system I've ever worked with had some sort of user service, for example. So whether that was included authentication or was just about identifying users by ID. And usually it's because that you need to have some sort of centralized repository for all of these users. That's the whole single source of truth idea. And so another central piece of this might be what's called a service registry. And there are a lot of different implementations of service registries. The simplest ones are basically just a hosted hash. It's like a Ruby hash as a service, where you just kind of like register all of your. It's basically a centralized configuration, right? So you have all of your services service names are the keys, and the values of that hash are either the URLs or some other configuration, protocol information that you might use to communicate with that particular service. And this way, when you use a service registry, all you need to do in every service when you deploy it is to configure the service registry URL or however you communicate with it, so that everything else can be discovered. But otherwise, the system is pretty decentralized. So for example, if we have this set of services in an e-commerce application, each service might actually have all of its, like each of its own processes for handling web requests, handling background jobs. So it might have its own sidekick and its own process for just running recurring tasks. And also notice that each service that we have here has its own data stores. So it'll have its own application database, Redis, and cache. And so you definitely don't want to share a database between multiple services if you don't need to. And there are a lot of reasons for this, and I'm going to go through a few of them here. I have a lot of them in my notes. So if multiple services share a database, you run into issues like who owns the migrations? Like which one of these services are you running RailsDB migrate on? And when you do run the migrations, does deploying this update and deploying this migration, does that require going through and rebooting all of the services that depend on that database? If your database has connection limits, you might end up running into those connection limits. So like, for example, Heroku Postgres, you have 500 connections that you can use, and that's it. Like, there is no amount of money you can throw at Heroku for them to raise that number. You can run into that very quickly if multiple services share a single Postgres database. And so each service also typically has different requirements for the data. And putting them together can have unexpected consequences. So let's say, for example, in our e-commerce application our e-commerce system that we were looking at a little bit ago, if a developer on the catalog service notices that calculating the average customer review on every request is very expensive because running aggregate queries on every single page load, right, that would get very expensive. So they add a column inside the products table to denormalize that, and you have the average customer review, and that's pre-calculated maybe once a day, once every, I don't know, every time period. And then now, instead of having to run the aggregate queries on every request, they're just reading another attribute out of the table. But then a developer on the cart service notices that the products table now contains the average customer review column. And they start using it in their responses as well, because for whatever reason, they have a use for it. But then the catalog team notices that running those calculations slows everything down, because those aggregate queries are very expensive. And updating the database millions of rows at a time, because you're probably running this all at once, that could slow down performance across the board. And so what they end up doing is that they extract that from Postgres and move it into something like a key value store that updates a whole lot faster, such as Redis. So they migrate the data and drop the column. But now the cart service that was using that column needs it, and it crashes because the column that they were depending on was removed. Depending on how much they've become to depend on that column, there might be no quick fix for that. And so you definitely always want to have a separate database for every single service, if you can. Another thing you want to do is you do want all your services to have their own Redis. So for example, if we're running Sidekick, we don't want to share a Redis instance with all of our other services to run the same Sidekick job, or to run different Sidekick jobs. Because if we misconfigure something, we're grabbing other people's Sidekick jobs. And that's going to get rough real quick. Additionally, you also want to have a separate cache for each service. So having a separate cache, excuse me, let me roll back. If you share a cache with multiple services, and one of those services constantly updates the cache with new data, and you're using some sort of least recently used cache invalidation strategy, that service is going to invalidate everybody's stuff all the time. So you definitely, in order to keep your cache hit rate high, you want to have a separate cache per service. And so now we couldn't really go any further without kind of bleeding over into the communications patterns between services. So that's where we're going next. And so the most common pattern that I've seen for communicating between services is to have some sort of machine-readable format, usually JSON, being sent over HTTP. If you're communicating with a Java Enterprise service, for example, you might be using XML. That's still extremely common. And in high-scale situations, JSON might be too heavy. It can be very expensive to serialize and deserialize JSON. So you might end up going with something like Message Pack or Google's protocol buffers instead. But let's say your user-facing web page builds an HTML page from all the data pulled from the user's catalog and cart services. So it uses the user service to identify you as a user based on your cookie data. The catalog service to show you the product catalog for your e-commerce application. And the cart service so that it knows what all items are in your particular cart. So also notice the names we're using. We're calling this user service because users are kind of specific. They're kind of a special case because we typically need user data for the sake of getting user data. But we don't call the catalog service, we don't call it the product service, we don't call the cart service the line item service. We're not talking about them as if they're just database tables. Those are the lower level details that these particular services revolve around. But if we start calling them by the names of what we would call the SQL tables that we put them in, all we've really done is distribute a database across multiple systems or multiple services using HTTP that we can't do joins on. But the catalog service here may have some overlapping data with the cart service also. So we're not doing it just for the sake of being able to do joins. We're doing it because sometimes there are overlapping concerns. Even if each service might need a separate view of the data, there might be some overlap between them. So for example, the cart service, when you add a product to the cart, it may actually reach out to the catalog service and say, hey, catalog, can you give me the information about this? The user's adding it to their cart. But HTTP doesn't fit everywhere. For one, HTTP is a point-to-point protocol, so you need to know who you're talking to. You need to, so anytime your service performs an operation that other services need to be notified about, you would have to reach out to them to tell them. And so at that point, whose responsibility is it? Okay, I'm on the right slide now. Okay, so if service A performs an action and B, C, and D need to know about it, is it A's responsibility to reach out to B, C, and D, or is it B, C, and D's responsibility to figure out through some other method that happened? One of the other problems with using HTTP for everything is performance. You either need to maintain a connection pool for every service that you talk to, Or you end up paying the cost of a TCP handshake, TLS negotiation, and TCP slow start for every single request you make to every other service. And it might not seem like a huge issue, but when you're making thousands of these requests every second, you might be surprised at how much of your time is actually spent in this initial process, in the protocol overhead. Also, HTTP requests typically require waiting around for the response, especially in a language like Ruby, where the standard and core libraries are optimized for synchronous I/O. If you don't care about the response, for example, you may want to ignore it for the sake of performance, but that's not, it's not really feasible because HTTP, when you send an HTTP request, you are going to get a response back. And with synchronous I/O, the return value of that call, for example, in the Ruby net HTTP library, is the response. And so let's look at an example. Conceptually, what we think of, this is what we think of when we say A needs to reach out to B, C, and D. We think that it's sending all these requests at the same time. But really, what's happening is A reaches out to B, sends a request, and then it waits for a response, and then B responds later. And then, of course, we send out a request. We sit there, we wait for the response, and then we get it back. And we do the same thing for our last service, and wait for the response. This can be a matter of milliseconds. It could be hundreds of milliseconds or even seconds. Asynchronous I/O is difficult to do in Ruby. So, like, if we wanted to send out all three and wait for the response for all three together, it's just not a really common pattern in Ruby. And it's actually kind of difficult to do. We end up having to write or having to use separate gems that are optimized for asynchronous I/O. And even then, we need to consider all the dependencies. So, for example, in this example, how do we remove the synchronous dependency on all these? Roll back. If we send a request to B, and the response of that is used in the requests to C and D. If we're using asynchronous I/O, we have to kind of mix patterns. We have to use synchronous I/O for one and asynchronous for the others in order to get the best performance. So if this is hard to do at the language level or at the API level, how do we remove this dependency, this synchronous dependency on all these? The most common is to use something like a message bus. And this also, so if service A doesn't talk directly to B, C, and D, but instead just pushes this information into a message bus that B, C, and D also consume, then A no longer has to know that B, C, and D depend on this result. We just kind of shove out a message that says, hey, this thing happened, or hey, I need whoever is responsible for this to do this. We're just kind of throwing data over the wall. And this pattern is known as publish subscribe or pub sub. Pub sub is kind of like a Slack workspace, which, like Mars, is inhabited entirely by bots. I actually built a demo of this using Slack as a message bus for this talk, but I had to cut it for time. I'm already cutting it close as it is. But if you want to see this, I'll try to post a screencast of it this weekend after I've had some time to decompress after the conference. So the pub sub pattern, publishing a message is like sending a chat message in Slack. Each bot subscribes to a set of channels. It could be one channel, it could be all of the channels, or somewhere in between. And will receive every message that comes through linearly, chronologically, I should say, hopefully. Ideally, chronologically. Don't depend on that in production. When the service or bot receives the message, it might perform an action, which could include updating some of its internal data or sending one or more messages in response back into the message queue, back into the Slack channels. And typically this is used for things like sending imperative messages, like the same sort of thing that you would use a Sidekick job for, or notifying other services that something happened. And this allows us to bypass HTTP's enforced request response pattern without rewriting our services around a paradigm that our language just doesn't have good support for at the moment. Another benefit of this is that your service doesn't actually have to be reachable over the internet. Nothing is making connections to it, so it's not receiving incoming connections. So it doesn't need to be registered in your service registry or anything like that. It doesn't need a domain name or a static IP address. It's consuming stuff from a known source. So this means it doesn't matter whether you run this on Heroku or some other platform, or it runs on a Raspberry Pi that sits on your desk. This is also awesome because the next time somebody responds to a bug report with "works on my machine," you steal their laptop and wire it up to production and start consuming production. So these are just a couple of the communications patterns that we went over. We have machine-readable formats like JSON being sent over HTTP. We have human-consumable HTML fragments being sent over HTTP, and communicating asynchronously over a message bus. This is not an exhaustive list. This goes way deeper and way broader than this. But this covers about 95% of use cases that I've used. And so now we're going to get into the trade-offs of using service-oriented architecture over something like a monolithic Rails app. One of the big trade-offs is latency. When latency is the amount of time that it takes to perform an action once, and throughput is how many times you can perform that action in a given time period. You can gain a lot of throughput by distributing your work across a lot of different services, but the more services that you need to talk to before a particular action can complete, the longer it takes. So what ends up happening is you're delegating work from your machine off to another machine to free up CPU cycles on your machine. And there's time involved in serializing this and sending it over the wire, but normally you gain a lot of throughput for that. And also normally this is typically on the order of milliseconds, so nobody might notice the increase in latency. But as your system evolves, this might grow into a whole lot of milliseconds as you add several layers of intermediate services. And when I say layers of services, this is kind of what I'm talking about. This is a service graph at Netflix. They have a few edge services, so like the ones you talk to are the ones closer to the left. I think the furthest to the right is the one labeled API. That's as deep as any of us go. The rest of that is all internal services. Everything, yeah, the whole right-hand 2/3 of this is their microservice soup. So another thing that you have to work around is your team structure when you go from a monolithic app to microservice architecture, is that you might organize your teams around the concepts of these services. There will likely be little to no overlap in each team's functionality, or in each team's responsibility, rather. So they'll probably be working on the same subset of services and not a whole lot of cross-pollination between them. So this can actually lead to teams being siloed, and so you have to keep that in mind and have some mitigation strategies to keep your teams talking to each other, so they don't become too insulated. And also, distributed systems are a lot of work. Once you start going down this path, you end up needing one or more people whose entire job it is to keep that entire architecture talking to keep those systems talking to each other. They end up coordinating with developers and managers to make sure that the interfaces between those services stay consistent, and help them work around different trade-offs that they'll need to make in their own communications patterns. One of the largest maintenance burdens of distributed systems is that you lose atomicity guarantees. And this is really just a fancy term for the entire thing happens or the entire thing does not happen. Usually inside of a SQL database, we would use transactions for this. But we don't have that when these transactions are now spanning multiple systems. So for example, let's say a user needs to add an item to their shopping cart. So you publish a message saying, hey, user A adds item X to their cart. And they're adding 2 of them. So they've clicked the quantity 2 button. And so, yep, there it is. There it is. All right. So they click that button. We generate the message in our web app. We send that off to our message bus, which then publishes it to both of these services, the inventory and the cart service. But then the inventory says, we only have 1. We can't add 2 to their cart. So that's not going to happen. And so we then have to implement what we call compensating actions, which is like that inventory service has to say, sorry, this isn't happening. and the cart service has to respond to that, and the web service might need to display an error message. So then you also have to, so what this means is you have to think about every single action that gets published through your message bus and how it can be rolled back. A lot like active record migrations. You have to write the up and the down. Another big thing is uptime. This is going to be a large trade-off because now because now the uptime of any individual service in your system is the product of the uptimes of all services it depends on. So in our earlier scenario where we had A depending on B, C, and D, talking to B, C, and D directly, if each of these services has 3 nines of uptime, that's 99% uptime, or 8 hours and 45 minutes of downtime per year, a service that depends on 3 others will then have a full day of downtime per year. If we add a 4th dependency, that's nearly a day and a half. And serial dependencies are even scarier. So in this scenario, if B blows up, A can't do anything. Even worse, if any of these blow up in this chain, none of the ones to the left can do anything. And so, like in this situation, assuming each service would have 3 nines of uptime, like 99%, 8 hours and 45 minutes of downtime per year, if we do count dependencies, then A goes from 99.9% to 99% flat. That is over 3.5 days of downtime each year, which is literally 10 times as much downtime as it would have otherwise. And this isn't meant to scare you away. Like, downtime is inevitable. You don't need to know what, but you do need to know what you're signing up for when you choose this sort of architecture, and so that you can allocate extra time and money on mitigation strategies for downtime. And so there is a silver lining to this. In a monolithic Rails app, running tests and deploying might take anywhere from several minutes to a few hours, depending on the size of the application. At my company, the time for one of our services, one of our smaller services, to run the CI build and deploy to production after we merge a pull request or push a commit is 29 seconds. When everything is much smaller and much narrower scoped, your tests, the time between development and production becomes much smaller. And so this sort of deploy speed can be critical, can be absolutely crucial when you accidentally deploy a show-stopping bug. And development and testing a single service on others can actually be really tricky. You may need to stub out some of your dependencies. If you think about all the times that you've had to use the VCR gem to stub out requests to remote services, third-party services, you now have to do that for your own service, all of your own services that you depend on. Sometimes this might mean that you deploy a development cluster to use, to use in development, and something else that, some other sort of thing to run your CI against, some other sort of cluster. So if you communicate with all of these other services asynchronously, though, through a message bus, it can actually be easier to test because you just need to test that you can respond to a given message. Once a message comes in, you perform that action, and then you can make assertions on that either that process or the result of that call. And so, for example, if you have if your cart service, you're working on your cart service and it has an add to cart message, you might want to ensure that a given product is then added to the user's cart, and that's it. That's the whole process there. And so so there are a lot more trade-offs to be made in moving from a centralized architecture to a decentralized one, and I would love to chat with any of you about them because I really enjoy talking about this. So come find me wandering around and let's chat about what you're working with. And that wraps up what I've got. There's still so much that I couldn't cover here, but I appreciate you all for listening to what I could. My name is Jamie Gaskins. You can find me on Twitter with this handle. And thanks, everybody.